This is an experiment concerning the applications of conservation of energy, and it was done for Mrs. Witt's class and Mrs. Kindle's classes several weeks ago, actually more like a month and a half ago. And we had a pretty good time. These were fifth graders, so they know a little bit more about energy and so forth than third graders do, but hopefully I've taken things out of it that the fifth graders had trouble with. Maybe we can get through this. One area of concern is that we're going to be timing steel balls rolling down ramps, and we're going to get fractional seconds. We're going to get maybe between 0.3 and 0.6 seconds, and we're going to be dividing those times into distances in order to get average velocities. So the kid needs to know how to divide a number by a decimal on a calculator and how to interpret the result. So let's get into this, and we'll see if you think it's too hard for a third grader to do. The conservation of energy, the theory is, of course, that if you roll a ball down a ramp, the kinetic energy at the bottom is equal to the potential energy before the ball started rolling at the top of the ramp. And two implications of that are that the speed of the ball at the bottom of the ramp doesn't depend on anything except the height that it started from. It doesn't depend on the slope of the ramp, and it doesn't depend on the mass of the ball. So if you start two balls, one's light and one's heavy, they should reach the bottom at the same time. So the experiment, as I'll show you in a minute, is that there's a ramp at a fairly low slope, like the one on the left. It has the height established by hooking the left side of the ramp to a vertical support, and ball is released at the top by an electromagnet, rolls down the hill. At the bottom it's going fast. The distance from the top, where the ball is at the top of the ramp, to where the ball is at the finish line, which isn't really at the bottom of the ramp, but we'll have to account for that, is divided by the time to get the average velocity, and this is multiplied by 2 to get the instantaneous velocity at the bottom of the ramp, and that is what determines its kinetic energy. And so what we're going to do is to try to measure the speed of the ball at the bottom of the ramp with this low slope like it is on the left, and then tilt the ramp up with a higher hook on the vertical support and move the starting point down the ramp to where the heights are the same. The initial height of the ball is the same. And then we'll remeasure and do the experiment, and hopefully the two speeds come out the same. They should if energy is conserved and all the other experimental variables are eliminated. And then this is Galileo's experiment, which is essentially to compare the rate of falling of a large ball and a small ball with the same set of conditions, the same initial height. The ball is released at the top of the ramp. The ball takes a certain amount of time to roll down to the finish line. The finish line is where the timer shuts off automatically, because I've got a little LED and a CAD sulfide photocell down there to shut the thing off. And then the distance and the height are measured in both cases, and then the speed is calculated for each case, and you compare the two speeds and you can see whether or not Galileo was right. And he should be pretty close to correct. So what we're going to do is fill out an experimental sheet, which, let's see, dropping ball, okay. Here's the experimental sheet. We'll give you the mass of the ball. I'll figure that out myself. And then what we're going to do is to measure the height. One kid will measure the height of the ball when it's on the magnet. Another kid will hold the button down so that the magnet holds the ball at the top of the ramp. And then we're going to measure the height of the finish line, and then we'll figure out what the difference between those two heights is, and that's the H that's used to determine what the potential energy is. Then in order to get the kinetic energy, we measure the distance from the finish line to the starting point of the ball, and that actually is done. It's all graded off on the ramp. You can just look at it and see what that is and write it down. Then we're going to release the ball by releasing the button on the circuit. The ball will roll down the hill. The timer will start running when that ball is released, and it will stop when the ball crosses that finish line. And the kid reads that time off the timer, and it's say between 0.3 and 0.6 seconds or something like that. So you write the answers down here, do it 2-3 times, and then we'll average them. We'll add those 3 up and divide them by 3 to get the average time. I don't know if they've had that concept yet, but it might not be too hard to introduce that. And then record the average velocity and multiply that by 2 by the calculator to get the instantaneous velocity. We'll do that for 3 different balls so we can get the Galileo experiment done and compare those instantaneous velocities. And then we're going to move the ramp down to the middle hook, so we get this situation, the one on the left, where the ramp is at a low slope, but the ball is still at the top of the ramp. In other words, it's released from the highest possible point on the ramp with it in this lower slope position. And we'll repeat the experiment, and then what we're going to do is we're going to move that starting point down the ramp by moving this point down here, the starting point down here, and then we're going to hook that ramp to the higher hook on the vertical support so it has a very high slope, the same slope as we had in the first experiment. And we're going to redo the experiment, and we're going to determine whether we think the velocities are the same under the same height conditions. So that's the crux of the experiment, and each kid will have one of these data sheets, and hopefully we'll be able to fill all these things out in about an hour. I think it's possible. We did it in the 5th grade, and we got probably 2/3 of the experiments done, but we've killed a lot of time trying to calculate the mass of the balls, which we didn't really even use. And I stripped that out of the experiment because I think it's too much for the kids. Anyway, so now I'm going to make a video of me doing the experiment and filling the numbers in on the form, and you can see if you think it's too hard for a 3rd grader or if you think they enjoy it. Doesn't matter too much to me if they get the whole thing, the whole concept. The kids have some fun. They might absorb a little bit of physics and a little bit of understanding what a velocity is and what the speedometer is reading and all that kind of stuff. Hopefully it'll be some value in this whole science unit to you. Anyway, thank you.